So this is lecture 17. We're starting the second half of the series of lectures. And today is kind of finite differences day. First lecture about steady state equations, Laplace being the outstanding example. We're in 2D, of course. We're doing partial differential equations. And it's that step up in dimension that makes these serious numerical problems. So if I just look here, so I'll describe the standard replacement, the Laplace finite difference equation. The 5-point scheme has the basic accuracy. We could upgrade it to a 9-point scheme with higher accuracy. The issues are the solution of that system. How much would it cost by direct elimination methods? And those are by no means ruled out. First, because they're so simple, and we're a lot of practice with Gaussian elimination. But then we can often save an order of magnitude in the computing time by some iterative method, well chosen. So I'll speak about some of these. I've just at this moment added the last one there, conjugate gradients. Let me say that these are all described in section 5.3 of the text. So section 5.3, in the chapter on numerical methods, and including conjugate gradients are described there. I'm not going to tackle conjugate gradients in the lecture. I've learned that they're a sort of, they're not difficult to program. They're very powerful, and quite an interesting history, actually. So this is the sort of area that I did my thesis in. Well, more the afternoon lecture, the initial value problems. But there was a lot happening. This was, I don't want to say how many years ago, but these issues were really coming to the front. And conjugate gradients was an idea which one of my advisors, Hestinus, provided. By the way, I was highly interested to see in Eric Mazur's lecture last week. I don't know if you caught the name of the chap whose papers he had read, which had transformed his life and transformed a lot of science teaching, actually. He's the outstanding science teacher in the country, one might say. Anyway, they were papers by David Hestinus at Arizona State, son of my hero, Magnus Hestinus. And at the same time, conjugate gradients were suggested by a man named Lanchos in Ireland, another outstanding person. Anyway, they're not an obvious idea. They're built on three-term recurrence relations. But what I was going to say about the history. I hope it's okay if I talk about conjugate gradients without actually writing the formulas up, because that would fill the board and we'd lose the lecture. Anyway, they give the exact answer in n steps. Oh, I can even tell you a little about the problem, of course. But anyway, it was discovered that they didn't at the end of n steps, numerical errors had spoiled it, and they had to take more than n steps, and it seemed like it wasn't competitive with elimination, which also finishes, right, at a finite time. So conjugate gradients, thought of as a direct method to get the answer after a fixed number of steps, didn't win, even though it was a heck of a smart idea. And then, so some years passed, and then a guy tried it, thought, well, maybe I should think of this as an iterative method. Do conjugate gradients get me close quickly? Because that's what we're looking for in iterative method. We're not looking to get to the exact answer. We're looking to get real close fast. And the answer was they did. And so they're back in favor, very much, conjugate gradient methods. I can even tell you with a picture what the problem is. Suppose well, you know that I'm going to be solving KU equal B, right? This K is sort of like the interesting issue now. What is it? This is a K, this is a matrix K in 2D, 2 dimensions. And the question will be, what does it look like? And of course, we hope it's going to be symmetric positive definite, and it will be. I mean, Laplace's equation is symmetric positive definite, and so we would expect the same out of the finite difference scheme. Okay, so that's our job, how to solve KU equal B when K is this 2-dimensional matrix. And I can hardly resist writing down, because that's like the main point here. But to describe conjugate gradients, maybe I could connect this. Do we remember that this is also a minimization problem? That here we have an equation, a linear equation, or a minimization, a quadratic minimization, right? Those are the two that go together. And we minimize some energy expression, which is a half of U transpose KU. That gives the second degree terms whose derivative is KU. And then, I usually put F on that right-hand side, don't I? Funny, I knew as I wrote B that it wasn't something, I'm so used to writing AX equal B, but now I'm KU equal F is the right thing for our square symmetric positive definite one. So you remember that you subtract the linear term is U transpose F. That was in an earlier lecture, and probably not a bad idea to see it again. That minimizing this quadratic is what gives that linear set of equations. All good. Okay, so what does this quadratic look like? Well, tell me, if K was the identity matrix, what would the graph look like? What would the graph of P of U? So this is the U1, U2, multiple U directions, of course. I'm only, on this blackboard, I'll stick with 2. And now I'm going to graph this polynomial, and it sort of looks like this it's a bowl. Remember, K is positive definite, so it's going upwards. And the minimum here, what's that minimum value of U? Where's the minimum in this quadratic? If I'm graphing, this is a graph of the surface P of U. It's kind of bowl-shaped. Where does the minimum occur? Well, according to us, it occurs at K inverse F. Right. So locating the minimum is the same as solving the system. That's the thing. We have a choice. We could think of it as a minimization problem, or we could think of it as linear system, and like every step we take is intended to, we could discuss it in this language or that one. And every step we take would make it simpler, closer to the solution. Now, I asked, what happens if K is the identity, for example? Well, not very interesting problem, of course, because we know the answer right away. But if K is the identity matrix, what's the shape of the graph? What's the shape of that cross-section? Circle. Right, it's a circle. And we have no trouble. I mean, if it's a nice circle, I mean, it's fantastic. Of course, one step will just go downhill and boom, we're at the bottom. No problem. But now a real K has what sort of a cross-section? What's the typical K that's not just a scalar multiple of the identity or it's an ellipse. It's an ellipse. And the axes, well, of course it's an ellipsoid, in n dimensions, but we're chiefly interested in the shortest and the longest axes. That's what really matters. And of course those are given by Well, they're related to lambda min and lambda max. So the ratio of these axes is, well, it's probably the condition number. Lambda max over lambda min, or maybe it's a square root or something. Okay. Now, why does the condition number make it harder? My idea is for you to see geometrically that we're trying to get to the bottom of a very narrow valley. And the narrower the valley, the narrower extended valley, the tougher the problem is. Because if I try to start downhill, let me kind of iterate, do what, imagine that we're sort of like we've reached some point on the valley and we want to, what happens is a typical iteration bounces back and forth. You know, you can't get an iterative method that's going to go directly to the answer. I mean, that would be too much to ask for. So what actually happens is you bounce back and forth across this valley, and it takes a heck of a long time. And this ratio is the problem. Well, so the idea of the conjugate gradient method is that, unlike Newton's method, which just keeps trying, Newton's method goes downhill, like steepest descent. That's the most obvious algorithm. Go down, you know, wherever you are in this thing, go straight down until you see what will happen if you go downhill? You'll be on some kind of a parabola, so you'll loop up again, and you'll say, okay, that's the best Newton step. Stop there. They go downhill from there. It'll loop up again down here. Can you? I don't know. I'm drawing this, but I'm not really seeing it. Then you go down again, and it loops up again, and then you get in this thing where you're struggling, just back and forth, you're struggling to get to the center. Okay. Well, so just in a word, conjugate gradients is a very good idea. That's the chief point. And the main point about it is that it works a little harder to choose the direction. And it chooses a direction that really is not just 1 degree away from the direction it just took. So it takes it takes a perpendicular direction in the K inner product. And that's perfect. So that's why you get there exactly. If this was really U1, U2, you'd get there in 2 steps. 2 conjugate gradient steps. You'd take the steepest direction, and then conjugate gradients, you'd grind through the formulas, and it would give you a really the right direction to travel for the second step, and you'd be there. Okay, so that's hasn't revealed the algorithm for conjugate gradients, but it's mentioned this highly important name, conjugate gradients, and also mentioned the central idea. And it gave us an idea of this, another look at this connection between the two. But my lecture now will really focus on this linear system. Okay. So let's come to, what's K? That's our question. What is the matrix K? I'm ashamed to say that the book didn't do a very good job of describing the matrix K. It discusses the solution of the system in that section 5.3 and quite brilliantly. But, well, forgive that. But it doesn't, it's just a couple of pages of description of the matrix. So I'll be doing a little more back in section 5.1. So I have to put plus 5.1 for the matrix. It just talks a little about it. So let's do the same now. We're replacing Laplace's equation. And I'm going to put minus signs in it. Why do I put minus signs in it? Because I want positive definite. And the second derivative is negative, so I put a minus and make it a positive thing. Okay. And I shouldn't say Laplace, I should really say Poisson, because I've got a right-hand side. Of course, the source term might come in the boundary conditions, not in the interior. Either way. Okay, so what's the system? This is in some region. Okay, so I create a grid. Already you see a limitation of finite differences. If we're in a square, finite differences are wonderful. I mean, the grid is just right. If we're in a general curved region, we're going to have a lot of thinking to do about these points where the grid hits the boundary. There'll be a headache. You can just predict it. And I don't think we need a headache this afternoon. Or at least it would take more time and away from the central issue of the lecture, which is the interior, which is nice and clean and simple. Let's suppose it's a square grid. The distance h both ways. H is delta x and also delta y, let's suppose. Of course, I could deal with unequal grids. Okay. Then what's the replacement for the Laplace equation? What's the discrete equation? Well, we've talked about very long about how to replace a second derivative, right? It's with a -1, 2, -1, right? In the x direction, a second difference replaces the second derivative. Now, for uyy, a second difference will replace the second y derivative, but it's a vertical derivative. Maybe I'll suggest that with a -1, 2, -1, writing them vertical. Okay, and then I put those together, combine them, and I have a 4 in the center and a -1 in the east, west, north, and south nodes. So that's the 5-point scheme. That's the little molecule, 5-point molecule. And it gives, I think, second-order accuracy because these are centered. So centered usually guarantees you that one step above the minimum accuracy. So second-order accuracy, and that's and it doesn't spread out very much, and so it's a small molecule, and it's going to be the same except at the boundary. So we certainly would like to, the model case, of course, would be for when the region is a square. Then we'll have no boundary problems. Well, we still have to think, what are the boundary conditions? So I guess I have to, there will still be a question at the boundary, and the answer to those question marks will depend on what boundary conditions are imposed. If we're imposing Dirichlet conditions, fixed conditions, you remember, like u equals 0, then let me impose that here, u equals 0. Wow, okay. And then maybe at this end I'll impose, so this is in the x direction. Maybe I'll impose in this direction the Neumann condition, the free condition, the derivative condition, which would be du dn in the normal direction, but that's x equals 0, say at this point. Okay. And let me impose u equals 0 at top and bottom. Yeah, that's a good idea. So u is 0 on all these sides. U is 0 on 3 sides, but not, just to give you some variety, the fourth side is a free condition, a condition on the flow rather than on the temperature. a condition on W, in other words. Oh, do you remember that we have we expect to have the same U matrix A coming to V, maybe I called it in, or E, either way, and going to W and to F, and this will be A transpose, of course, and this will be, in this case, the identity. And you remember the continuous version? This was the gradient, so it was the gradient of U, and C was 1, so otherwise I'd multiply by something, and then this was minus the divergence, and that equaled F. That's our equation in our standard framework. And now the problem is make it discrete. Well, we've already indicated how we're going to make it discrete, and then solve it. Okay. So I don't think we want to spend a long. What will K look like? I mean, all right, this is our pattern, but here I've directly said what are the numbers. So how many? Let's see. What size will K be here? I guess it's the number of. Here we know what U is, so those are not unknowns. And here we have a boundary condition. So we can relate that to this, and we can relate that to this. So actually, I think it's only going to be 4 by 4. And maybe we could even write down what K looks like, this 4 by 4 K. I'd have to number the nodes, of course, to know what I'm doing. So let me number by rows. Row 1, row 1 and 2. These are the numbers of the mesh points. U1, U2, U3, U4. Okay. So what's the replacement for the x derivatives? For the x derivatives. So here's my matrix K, and it's going to be 4 by 4. Because it's going to multiply U1, U2, U3, U4. Okay. All right, let me look at U1 here. Look at that point. Around that point, in the x direction, oh, well, maybe we can put the x and y together. Probably we can. You do the whole 4-point thing at once. So here we're looking centered on point 1, where we would normally have a 4 there. Here, hang on a moment. Let me make U equals 0 on all sides to make it all clear at the start, and then I'll fix it. It'll be the difference between our fixed and our fixed free. Going back to the very first lecture, guess I'm hoping that you're keeping in touch with that first lecture. Okay, fixed, everything fixed. I guess I should say fixed 4 times here, because all 4 boundaries are fixed. Okay, then what? Then we have around here, we have 4. Minus 1 is multiplying its neighbor. Minus 1 is multiplying the neighbor above, and that's not involved. U4 is no diagonal. And similarly, U2, around U2, there's a 4, and its neighbors are number 1 and number 4. And then around U3, at U3, there's a 4. Its neighbors are 4 and 2. And this guy, his neighbors are that and that. Okay. That's my matrix K in this small example. What are its properties? Suppose I had... sorry? Did I mess up here? This row you're speaking about? For U3, 4 and yes, and it's oh sorry, did I get the wrong neighbor? certainly did. It better come out symmetric. Right. Thank you. Thank you. Absolutely. That's right now? Yeah, yeah. Symmetric. Absolutely. Thanks. Catch that on camera now. This is the right one. Okay. What are the properties of that matrix? Well, what do you figure? Symmetric. We just made it right. Positive definite. You bet. You bet. It's coming from our old A transpose A, and we could figure out what A is here. I'll put it in the notes for the lecture. Because here's a case where we can go directly to the guy here. So it's positive definite for sure. And by the way, if I just showed you that matrix and you didn't know anything about where it came from, would you know that this was positive definite? Yes, because so one test would be eigenvalues. Well, usually eigenvalues would be a messy test. In fact, I've forgotten offhand what the eigenvalues of that matrix are, so I'm sure they're quite neat. But I know they're positive. How can I tell that looking at that matrix that it has positive eigenvalues? Because the diagonal is dominant, right? So here's a fact, that all the eigenvalues of a matrix, if the diagonal dominates the sum along the rest of the row, and I'm willing to take absolute values of all those other guys. So I would say the rest of the row gives me 2, but the diagonal is bigger, it's 4. And if every diagonal is there, then no question the matrix is positive definite. In fact, I could even say something about where the eigenvalues are. There's this sort of, well, in this case, let me do this case first and then speak more generally. I have a 4 times the identity, so let me mark the 4 here. That's where the eigenvalues of 4i would be. And then the eigenvalues of this off-diagonal stuff, how large could they be? Just look at those minus 1s. Do you want to make a guess on how large or small? They probably have plus minus diagonal, actually. Plus minus eigenvalues. Any guess on what the eigenvalues, how big could they be if I ignore the 4s now, just look at the minus 1s? 1 or 2, I think, could be as big as 2. Actually, I can think of an eigenvector for eigenvalue 2. There, can you see it? I think. Oh, no, maybe not, or yes. I was going to take the all ones vector. Yeah, I would say if I took the all ones vector, I'd probably see that it was an eigenvector, and its eigenvalue would be 2. So from this 4, I could go like 2 in either direction, from 2 to 6. The eigenvalues are between 2 and 6. And I think it happens that 2 is an eigenvalue here. But I know the eigenvalues are between 2 and 6, so I know they're positive, so I know the matrix is positive definite. I know Gauss elimination will be great, conjugate gradients once, and all these other ideas work well for positive definite symmetric matrices. Yeah. Do you want me to take another second on that little location of eigenvalues? Because it's quite a neat result that is in the text somewhere. It's Gershgorin, some Russian guy, observed that if I took a matrix, then he has a bunch of circles. And the Gershgorin circles contain all the eigenvalues. And it's easy to prove. It's actually in the linear algebra book, too. So where are those circles, of course? Well, they're circles around the diagonal entry. Let's call that AII. So here are going to be the circles. This is the complex plane because Gershgorin isn't only talking about symmetric matrices. So here's the real axis. Here's the imaginary axis. And let me suppose it's a real matrix. So there's AII. That's the center of circle number I. Now, what's the radius? Then I've told you the circle. The radius is that sum of stuff on that row other than the center guy. It's the absolute, you add up the absolute values of all the others, and that gives you the radius. So you add up the absolute values of all these entries, it gives you a radius, and suppose it's that big. And then there's another circle for row 1 and 2 and all. So we have a bunch of circles. Centered at like A11, A12, A22, that might have been A33, maybe here's A44. What could we learn if those were the Gershgorin circles? Well, I guess all we can learn, or what we learn immediately is that all eigenvalues are between what and what, if they're real. In other words, all eigenvalues are in one of those circles. So certainly all eigenvalues are somewhere between that end and that end if they're real, or in this funny shape if they're not real. In the symmetric case, we know they're real. So we're only concerned with intervals of the real axis then. Could this matrix be, here's an interesting question. Bring out the key of the little bit extra about Gershgorin. Could this matrix be positive definite? It couldn't. And do you know why not? Sorry? There's a circle there that doesn't even have a chance to give us a positive one. And the Gershgorin result is that does every circle have an eigenvalue? I'm pretty darn sure that that would rule out positive definite. Yeah. I'm pretty sure. I've lost absolute confidence here. Because I don't, is it, now I guess it's not true that every circle must contain an eigenvalue. Well, anyway, Gershgorin it's kind of a little fun. It's very elementary, and it gives quick information about eigenvalues. So in this case, all the circles would be centered at 4, and they would all have radius 2. So they're all the same circle in this example, and the symmetric matrix means that I only have to think of real eigenvalues. They're between 2 and 6. Okay, good. Okay. Now, I guess the next step should be to try to visualize what K becomes in other cases. This was a small case. What would K look like in the, let's change that back to this other boundary condition. What's the effect of that? Yeah. Can you tell me what the effect of that is? So what is this little molecule look like at a, maybe this is a good way to do it. What happens to our molecule when this guy, when the boundary condition here, this is not an unknown anymore, it's not a known anymore. What's known is a derivative. So it's known that this is the same as that. That's all, at least that's our approximation. So our approximation is that that's the same as that. So what happens to our molecule? It loses an atom. Oh, this is kind of cute. But that's as being the same as that, left only 3 there. Is that right? I think that would be. So I think that if next to 1 and 3 we have a flow condition instead of a fixed condition, then I think next to 1 and 3, this is only a 3. So next to 1 and 3. So let me look at number 1. So this had This had originally a 4. You remember there was a 4 there. And there were minus 1s, but this was a known, so it didn't show up. A minus 1 there and the minus 1 there. But now this guy is not a known. It's only known that it's the same as that. So that becomes a 3. And also number 3 becomes a 3. Now, is that matrix, I always get to ask you this, is that matrix is still symmetric? Is it still positive definite? Yes. What can you say about its eigenvalues? I can tell right away that all eigenvalues are larger than what? 1. Good. They're score in circle. I don't believe 1 is an eigenvalue now. But now, okay. So, but that's still fine to work with. We totally have to deal with those. We might have the same. We might have 0 slope here. We might have 0 slope here. What would happen if we had a few more 0 slopes? Then these 4s start dropping to 3s and even 2s in some cases. Oh, tell me what happens if I have this condition at all, a normal derivative 0 at all. All edges free. So free, 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 free square here. Then what are the entries of K? What are the diagonals in K? So if it's free, 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 or what's going to be, for example, here? They're all down to 2, right? They're all down to 2. Now I'm not going to allow that the name K anymore. Why not? Because it's like our B matrix from the past. It's what? Sorry, it's now singular. It's now singular. Physically, it's singular because, of course, if I'm giving the derivatives on all the edges, then I could only know the answer up to a constant, right? If a constant would solve the homogeneous equation. A constant is in the null space. Of course a constant's in the null space. The vector 1, 1, 1, 1 is in the null space of that matrix. Yeah, so we don't, you need something to hold the whole system down, in other words. If it was like a mattress, I mean, it's kind of a line of springs is now jumped into a two-dimensional mattress. Is that the best word to pick for, I'm imagining springs in both directions? Or cot, maybe? Then if there's nothing fixed at the edges, of course, it's completely out of control. So we'll go back to the good one. All right, K. Okay, so the good one was something, well, the very simplest one was all 4s. Okay. Now, one more minute on this before I speak about iterative methods, because we just have to visualize the equation. Jump up to a bigger system, 100 by 100. Say 100 by 100 interior unknowns. So 101 steps here, 100 in the middle, and a guy on the left and a guy on the right. Okay, what's the order of K? So we have now, so this is like a thought experiment because I don't plan to write down the matrix. So we have 100 by 100 interior U's. Okay, so the K has size what? 10 to the 4th. Right, 10 to the 4th, 100 by 100, n squared. N squared. Let me just call it n. N by n. N times n. Unknowns. So the size is n squared. Okay. Now, n squared by n squared. Now, in a minute, I'm going to have to ask you what are the numbers in K. Oh, yeah, I already have to begin to ask you, what does K look like? Yeah, can you tell me something about what K looks like? I'll order those unknowns just as I did here, a row at a time, then the next row, then the next row, then the next row. But you see the problem. that we have a 2D problem. We have a two-dimensional arrangement of nodes, and we've got to put them in a line. We've got to number them from 1 to n squared. And it's sort of the curse of dimension. Our matrix, a row of our matrix is got to deal with not only the row of the thing, but the guy above and below. So anyway, what can you tell me about K here? So big matrix, what's a typical entry on the diagonal? 4, still. 4 sitting on the diagonal. So I'm somewhere in the middle of the matrix, let's say. 4 is a typical guy on the diagonal. And what else is on that diagonal, on that row? What's on the row along with the 4? Well, it's just coming from the molecule. Yes, I'm in the middle here. I'm in the middle of this big square, so I have the true molecule. No boundary stuff is messing me up. So what do I see then on that row? I see just to the left of this 4, I see a minus 1. And just to the right, I see a minus 1. So that's like tridiagonal. Then quite a distance. How many spaces over to the guy who's in the U that's in the row above? Yeah, n, like 100. And 100 in this direction. Sorry? If I'm right at an edge, a boundary. If this guy was real near, I mean, I've drawn it sort of as if it didn't quite hit a boundary. If my center node was next to a boundary, then that might change to a 3. Or I would certainly lose the minus 1 or something. But there's a row that's sort of well into the middle of things. Now, so you see the main idea of the matrix is we've got 4s on the diagonal, we've got tridiagonal, but then we've got these diagonals which are far off. That distance is exactly as you said, n. The bandwidth is n. The matrix has a band of width n. Because it took n counts before we got to the end of the row, started the new row, and got to the node above, or the node below. This is n steps to get from here to here. Okay, so suppose we use elimination, which we certainly can. What will happen? What will happen? And in my message about this lecture in advance, I created the matrix K for some boundary conditions, and I think I looked at the inverse just out of curiosity, but I couldn't see anything special. I should have looked at L and U, and tell me about L and U. So if I do elimination, do the L and U factors look like this? The triangular part look like that, and the upper triangular part look like that? That's the key question. Imagine doing elimination on this 5-diagonal matrix. And as you've said, the diagonal isn't. It might have a break here where a row ends and the next row starts. There might be a boundary anyway, but it's got 5 diagonals, but they're not all minus 1s. I mean, we have to hit the end here somewhere. If they were all minus 1s forever, well, of course, then the matrix would only be semi-definite. But the boundary condition saves the positive definiteness. But, come back to this point, what about elimination? Because people certainly do elimination on this. And what will be the problem? What's the cost of elimination, and where do we see it? what's the cost, elimination cost? So size n squared, bandwidth n, or half bandwidth, you might say, is n. This is n, this is n squared. What's the cost, first of all? For a matrix, if we know it's a banded matrix, and we know the size is n squared, and we know that's the order of the matrix, and then we know the bandwidth. The general rule is order times bandwidth squared. That's the elimination for elimination count. That's why a tri-diagonal matrix is so fantastic. Its bandwidth is only 1. I mean, we're proportional to there's a constant here. We're proportional just to the size of the matrix for tri-diagonal. Now ours is not tri-diagonal for sure. And we get n squared times the bandwidth squared times, so that's n, we get n to the 4th. Operations for elimination. And in 3 dimensions, oh, can you imagine this is in 2D? This is 2D for an n by n grid. Do you want to tell me what 3D would be for an n by n grid? Well, what's the size of them 3D matrix? How many unknowns in 3D? N cubed. And what's the bandwidth? N squared, right? Because you haven't finished that row until you've got not only to the one above, but the one in the other dimension. So it's n squared twice, making n 7th. So now you're getting to like serious tax cut here. The end of the 7th is, and what's coming back to what's happening in elimination. As I do elimination, the band is preserved. I'll never have to do any elimination down there, right? The band will stay there and nothing will ever show up there. But all this big band of zeros between that -1 and the next one, about 99 zeros, that will all fill in. That's the problem. You get tremendous fill-in if you just do Gaussian. You see what happens when you subtract multiples of one row from another? It starts filling in these otherwise zero things. And of course, the symmetric thing, the L transpose, has got the same. And you'll see it. If you would just take the matrix in the message about this lecture and do LU, which I should have done before I sent it, you would see that it fills in. You could hope that some of the fill-in numbers are not too big. Oh, and I can tell you right away the key iteration idea. Compare it with exact LU. So I'm going to compare exact LU with incomplete LU. So exact LU is what? So this is perfect to make this point. And this incomplete LU, ILU, as I believe, is a favorite. It's people like to work with it. So if we don't have time to discuss the subtleties of over-relaxation, which was the hot. So David Young wrote a thesis at Harvard in the 50s with Garrett Burkhoff, in which he studied this over-relaxation idea. I haven't explained it's an iterative algorithm. And that was a big success for a while. Then there were other competitors. Conjugate gradients looked like it was dead, got revived. So it's in there. And then a guy named van der Vorst in Holland came up with this incomplete LU. Simple idea. And so that's what I'll describe here because it's so intuitive. And it, you know, it connects directly without any fancy formulas. Maybe you're seeing, though, from this brief account of the history, a rather important point, that everybody's got a shot at this thing. Like, you don't have to be Gauss to devise an iterative method which could be quite a good one. I mean, van der Waals is a sharp guy, but he isn't Gauss, and it's made a major difference. So that's, let me tell you what it is then. Okay, so complete LU. This is elimination. This is Gauss, okay? Just you do LU. You solve, you factor in and you solve LU, U equal F, right? So this is our A, U equal F. A complete is A equals LU, of course. And then how is it you solve this system? If you knew the factors, then you could forget A. You only need to remember L and U. And how would you solve that system? Just reviewing the basic idea of elimination. How do you, what good does it do you to have done the work of elimination and have got to L and U? How would you solve that system there? By L first, right? It's this, you would solve for this unknown first, say L, C equals F, and then C is this, so then you'd solve U, U equals C. This is forward elimination, this is back substitution. Forward elimination, as you go forward down the matrix, you're changing the original F into some C. So the C is what's left when you're ready to start back substitution. Back substitution is back up with the U matrix. Okay, in other words, two triangular systems. That's fast. The cost was finding L and U. The cost was this factorization. Because you see why this number might come in, this n squared times, this size times bandwidth squared. Why is it size times W squared? Because this row has length W, and you have W possible things to eliminate below. So how much does it cost to begin elimination on that first column? You're taking multiples of this row of length W from these W rows, so W squared to get this guy. And then you're down to the next size, and there's a W, and it's got W, and it costs you W squared to get that column right, and so on. So it's size times W squared. Of course, U and L have that same bandwidth, W, but back substitution would just be size times W, not squared, and so on. Okay. So can you guess what incomplete LU is? Seems so natural. Well, of course, it's natural to think of it. It's not clear that it would work. What you do is you go forward with L and U, but for entries that are small, you set them to 0. So that hopefully there's a lot of small stuff in this fill-in. And you say, the heck with that. So incomplete LU is A is approximate. This is an L approximate, U approximate. In fact, it equals this plus some error, the stuff that you set to 0. And there's a whole lot of freedom, clearly. You have to decide, okay, what's small, what's not small. Okay. So, how do you use this? Well, iteratively. So the idea now is I'll solve L approximate, U approximate. These are nice ones with lots of zeros, times U, my n plus first guess. Well, let me use a different letter. I plus first guess is I'm going to put this part of the E part on the other side as minus E, U on the old guess, and then I'll add in the F. So now we're seeing iterative method, and we're seeing one iterative method in particular. And let's suppose it converges. Does it converge to the right answer? If it converges, do we get the answer right? Sure. If this approaches, if U approaches some limit as I goes to infinity, then this approaches U, and this approaches U, and this approaches L approximate, U approximate, U, and this is minus E, U, and this is the F, and I bring that over, and sure enough, I have KU equal F. Yes. Good. So now, you see every iterative method, there's two requirements, two conflicting goals here. One goal is that this part should be easy to deal with. We want this to be easy. And the second goal is we want this iteration, this convergence, to be fast. And those are in conflict. Because what's going on up there? The convergence is immediate. I put everything on the left side. I did it all exactly right. In one step, I get the answer. But that step isn't easy, isn't quick. It's the n4th or n7th. Now, this step, doing it this way, it'll take some convergence. In fact, we aren't going to run it to the limit either. We want to get within some tolerance of the answer. That'll stop our iterations. But do you see that it is now easier? Because these L approximate and U approximate are triangular. They're maybe just the three diagonals that we would have hoped for. Maybe I'll put those in yellow. So for the L approximate, we might just keep those numbers thinking, well, those are probably the biggest. Or if we have to keep maybe one more, because it's significant to have 4 diagonals, but we don't have n diagonals. We don't have 100 diagonals in L, and similarly in U. It's E that's got all the other diagonals in it. But so E I could rewrite as A minus L approximate U approximate. Do you see that you see the idea? The idea is to try to take as much of A as you can, as much of K. I should be saying K, shouldn't I? I've fallen in my trap again of thinking of everything as A, but really K is my letter. I want to put as much of K, I want to put the heart of K on the left side without making it hard to, without making each iteration step hard, because I'm going to iterate maybe, let's see, if n is 100, I would maybe hope to do it in like 10 iterations. So that would be 10 iterations, like square root of n or something. This is where you get in the calculation. And what, I'll just end with a question. What controls the number of iterations? Or convergence at all? I think you answered that question before. If we subtract this equation from this one, we get the error equation. So if we subtract this from this, we would get the same matrix LAP, UAP, times the error at step I plus 1 equals minus E times the error at step I, and the F's would cancel. And I could put I could bring all this, I could put EI plus 1 as the inverse of this times the E. Every iteration is multiplying by some matrix, which we never actually compute, but we know that's what we're doing. The error is getting multiplied by that matrix. And so what's the deal on convergence? What would make that convergence fast? If I'm repeating, multiplying over and over and over by this same matrix to bring the error down, what's the requirement on that matrix? The eigenvalues, yeah. The powers have to be getting smaller, and we hope that the eigenvalues are our best guide to those powers. So the largest eigenvalue had better be below 1, or we don't have a great idea here. We hope if it's down as low as 0.9, that's quite good. Gauss elimination Gauss-Seidel and over-relaxation might produce in a typical problem, Gauss-Seidel might produce an eigenvalue of maybe, let's say, 0.99. So that takes quite a few iterations to get down to something. Over-relaxation might give an eigenvalue of 0.98 or even 0.97. That would be a tremendous improvement. And incomplete LU, I don't know. Depends how close to complete it is. So I'm going to stop there with this recap. This is the type of matrix that we're looking at. Those are some of the ideas that have gone into iterative methods, plus conjugate gradients. And finally, let me mention one other idea. If it really is a square, then you would expect some special methods, Fourier-related methods, FFT-related methods to be successful, and they are. So there are special algorithms if you have a nice square rectangle, because you can take Fourier transform then. So those are the fastest of all by a long shot, but of course they're only for squares. And then you might try to build up your region out of squares. So that's called domain decomposition, and there are conferences every year on domain decomposition, where you take your domain and take nice pieces, and then of course you have to make corrections, because if you solve in one piece and hold the other piece constant, then there's a correction to make. So I could add domain decomposition to our list of ideas. Well, so that's a sort of give you a sense of some of the thinking that's gone on in the numerical analysis community, numerical PDEs really, but it's matrix problems, on this type of steady state problem. And my second lecture at 3:30 will be quite different because the equations are very different. We're moving forward in time. They're time-dependent problems, and stability becomes the big issue. Here, speed was the issue, but there, the question is stability. Can we, well, and speed, of course, can we take big time steps and get where we want? Or will big time steps give us a blow-up situation? How big could the time step be? That's so that's the central question for lecture 18. Okay, let's take a break and any questions. And if anybody has any success with that curious matrix problem, please tell me about it. I'm looking for a good argument there. Okay.